We've talked in the past about the structure of a linear function. So we've had like y equals b plus mx. So here's our kind of basic linear function. Y is equal to b when x is equal to 0, and y increases by m when x increases by 1, or we'll say every 1 unit. So here's our start. So what the reason I write this is that this is the order that we think about it. Y equals b when x equals 0, and y increases by m every 1 unit, or when x increases by 1. Then we can have variations on this theme. And the reason I'm talking about linear functions is because I want to talk about exponential functions. And all that happens when we trade from linear functions, patterns of repeated addition, where everything is simple, is that we trade for a pattern of repeated multiplication. So instead of using multiplication, m times x, to indicate the repeated addition, we write an exponent, b to the x, to represent repeated multiplication. So in this format, we say y equals b when x equals 0, and y increases by m every 1 unit. The slope, when we write the slope, that's the unit rate of change. The unit rate of change. But we can also think of this by splitting up the rise and the run. We do know that slope is rise over run. And so we could, if we have a separate, if we want to separate the rise and the run, if you want, for example, a different run, like a table of values has a different run, we can set it up this way, where we say y equals b when x equals 0. And here y increases by the rise. Every run units. Now, in this case, once again, we're starting off with an intercept. What's going on with y when x is equal to 0? If we want to change that to a different value, if we want to shift this to have a different starting point because our information is different, we might say that y is equal to y naught plus rise over run times x minus x naught. And this changes our opening. In this point slope version of things, we would just trade y equals b when x equals 0 to y equals y naught when x equals x naught. And then the other part's the same. And y increases by the rise every run units. So what's going on with a linear function, we have a pattern of repeated addition, and we indicate repeated addition with multiplication. So a linear function is repeated addition. There's that repeated addition is where we say m times x. Add m x times, add m a bunch of times, and that would be x times. The reason that we like this is that it's really easy to scale because we're dealing with the proportion. In a linear function, the rate of change is constant, so the ratio of the rise to the run is constant. So in a linear function, the ratio, the slope is constant. And the slope is just the ratio of the rise to the run. So this ratio of the rise to the run is constant. This makes it really easy to scale up and scale down. That's why linear functions are so easy. That's why this is the default mode of human approximation and calculation, is the default thing that we do. So we think linear. Because if we have a slope, if the slope is equal to 2, I can read that as 2 to 1, or 4 to 2, or I spelled equals wrong. Or 4 to 2, or 20 to 10, or -2 to -1. Because it's just a ratio, it's really easy to scale up and scale down. So if we notice that our population is increasing by 20 every 10 years, that's 2 per year, or 4 in 2 years. If I wanted to know what would happen in 100 years, I just multiply by 10, 200 in 100 years. That's 2 to 1. It's a 2 to 1 ratio. That remains constant. And this is why we like linear functions. Exponential functions operate differently because exponential functions have a pattern of repeated multiplication. So our simplest form in an exponential function the simplest form of an exponential function is to say y is equal to a times b to the x. Y is equal to a times b to the x. The parts here say that y is equal to a when x is equal to 0. Remember, a 0 exponent indicates is just 1. Everything that's non-zero to the 0 power is equal to 1. 0 to the 0 is indeterminate. It all depends on what we want it to be. But the description is still very straightforward. We'll say y is equal to a when x is equal to 0. But instead of y is increasing by m, we'll say y is multiplied by b every 1 unit. Y is multiplied by b every 1 unit. This repeated multiplication is indicated with the exponent. So an exponential function is repeated multiplication which is exponents. And there's our repeated multiplication. summarized with an exponent. This is where we're multiplying by b every 1 unit. B is the unit multiplier, just like slope is the unit rate of change. What's happening when x increases by 1? B is the unit multiplier, where m was the unit rate of change when x increases by 1. But like we saw yesterday, what if we have something that's increasing at a different interval? We have a multiplier that's being applied at a different interval. So we want to separate the rise and the run. What's it going to look like if we separate out the rise and the run? If we divide into, well, it's not going to be division. What's going to happen if we want a different run? We observe a multiplier, but it's not a unit multiplier. So I wanted to color code this. So we set up a similar, set this up in a similar way we did with a linear function. Now I wrote it as rise over run because we always put the run underneath the rise because it's just being multiplied by the x and we can move stuff around easily. But really, it's the x that's being divided by the run because that variable part is saying how many times you do this. How many times you add the rise? X over run times. That's counting the number of times. So that's a little bit of a change. So we're going to write y is equal to a. Then we're going to say, what are we doing to the a? We're multiplying it by m. I usually use m for multiplier. And we want to do this every k units. So we say x over k. I usually use k for my interval. So m is like the rise. That's what we're doing. K is how often we're doing that thing. Notice that in multiples of k, when x is equal to 0, I have multiplied by m 0 times. 0 divided by k is 0. We've multiplied by m 0 times. We're starting off at a. So here, y is equal to a when x is equal to 0, and y is multiplied by m every k units. So I've separated out my multiplier into the analog of a rise and a run. And we are still indicating repeated multiplication with this exponent right there. Now, if we wanted to shift this, if we wanted to start off at a different value, instead of knowing what's going on at x equals 0, maybe it's not relevant for us to know what's going on at x equals 0. We only care about what's going on between x equals 11 and x equals 50. So we don't care about what's going on at x equals 0. If I want to shift this to a different starting place other than x equals 0, I do the same thing what we did up here. Just subtract our new starting place. So I would just say y is equal to, and instead of a, I'll say y naught times m to the x minus x naught divided by k. So the description here, this equation is trying to communicate to you that y is equal to y naught when x is equal to x naught. And y is multiplied by m, that's right here, times m. Every k units. It's the same structure that we had in a linear function. but the rise and the run aren't in the same fraction now. Because in the linear function, we weren't dividing the rise by the run. We were dividing the x by the run to see how many times we're doing the operation. Any questions? And this is a function representing repeated multiplication. Repeated multiplication is summarized with exponents, and there's our exponent right there. Same place it was in the other two. Just like a linear function is repeated addition, summarized with multiplication, an exponential function is repeated multiplication, summarized with exponent. There are other operations. There's a repeated exponent operation where you put a superscript on the left side of the number. Instead of a coefficient, you raise that up to a superscript. That's a different operation. That would be repeated exponents. Side note, if we write 2x, that's repeated addition. If I write x squared, if I put a superscript on this side, that's repeated addition. If I write 2 as a superscript on this side, that's going to be x to the x. So that's repeated exponents. That operation has a name that I can't remember. Also notice there's another place that I can put the 2. If I put the 2 as a subscript on the left, that's just going to be repeated this operation. There you go. That was DVD book. We'll cut that. So the reason that linear functions are so simple is that the defining characteristic, the slope is constant. That's easy to deal with. A slope of 2 is 2 over 1, 4 over 2, 20 over 10, 10 over 5, -2 over -1. That's really easy to change. Exponential functions, it's more difficult. Okay, so notice if we're multiplying at different intervals, if I want to trade m to the x over k, oops. So if I have a unit multiplier, if I want to figure out the unit multiplier from some k interval multiplier, don't worry about where we start. This is just tracking the change what we're multiplying by. If I pull the x from and just look at the base, I have m to the 1 over k. So if I have a k interval multiplier and I want the unit multiplier, b is going to be our unit multiplier. It's like our m with a denominator of 1. Well, I have to realign some stuff over here. I can rewrite m to the x over k as m to the 1 over k raised to the x power. So we have to use radicals to change our interval. We need radicals to adjust the interval. That's why it's less easy. So for example, if we have a description that says multiply by 2 every 10 units, if I want to know what happens every 1 unit, since it's multiplication, I have to undo that with some radicals. I need a 10th root of 2. If it was addition, if we're just adding 2 every 10 units, then it's just 1/5. We can just change the ratio. Simple. But since we want to multiply by 2 every 10 units, to undo that, I've got to take 2 to the 1/10 to find our unit multiplier. And I don't think we teach 10th roots anymore. Did you learn your radical table? No, I didn't either. No one did. But you used to have to look that shit up in a book. It was ridiculous. It's like, oh, what's the natural log of this number? Hang on, let me look it up in a fucking book. And now we just like type it into our calculator. Or even just ask Siri what's going on. But if we want the unit multiplier, I've got to take the base 2 and raise it to the 1/k power. And I do not know my 10th root. I'll just take 2 to the 1 divided by 10. So 1.07170718. That's a ridiculous 5 significant figures. Actually, I was going to write this as a percent, so. Let's just do 4 significant figures, because that's still excessive. Any questions? The other thing that we want to notice from this is we want to remember that multiplication is how we increase by a percent. So when we say multiply by 2, that's another way of saying increase by 100%. So multiplying by 2 every 10 units, we just found is the same as multiplying by 1.072 approximately every 1 unit. When we multiply by a number, we're also increasing by a percent. So we might say something like increase. We might translate this to increase by 7.2% every 1 unit. Just like multiplying by 2, we might say increase by 100% every 10 units. Increasing by 100% every 10 units is the same as increasing by 7.2% every 1 unit. The point is, we have to use radicals to change the multiplier and the interval, rather than just changing a ratio. That's why we like linear functions. Questions? This is how I like thinking about linear and exponential functions. They have that same structure. A linear function is a pattern of repeated addition that we summarize with multiplication, and And an exponential function is a pattern of repeated multiplication that we summarize with exponents. Or if we're writing single line syntax, exponents. The interesting thing here is that we can change to whatever base we want. It's not as easy as doing that, changing the denominator in the slope. Changing the ratio, very simple. If you have a particular denominator that we care about, very simple. If we want to change to a different interval and figure out what the multiplier is in an exponential function, we have to do some of this stuff. So another base that we like to use we might want to use a multiply by e. We want to know how often we multiplied by e. This is useful for things like continuous compounding and stuff. Same. So here we're looking at continuous growth. We've talked about E in the past, and we talked about increasing the number of compoundings was increasing our output, but it was limited, and it was limited by this. E is the limit as n goes to infinity of 1 plus 1 over n to the n. And here's just the R version of that. So here, to describe what's going on here, when we write this E, we're thinking of continuous growth. We're continually multiplying. And R is the continuous growth rate. I said increasing, and this is an exponential function, so the increase is by a percent, but it's a continuous increase of R percent. And this is still happening every 1 year. And we might want to do the same thing. We might want to translate between our unit multiplier and our continuous growth. If something is nominally increasing at 10% per year, like we had yesterday, what is the continuous growth rate? Because we might want to use that in our problems. So here, let's just look at the multiplier part, b to the x. And I want this to equal e to the r times x. Well, I'm going to do the same thing. I'm going to take the x and separate it from the e to the r part. This is an e to the r to the x. So I just want to set up e to the r is equal to b. So if you're given the continuous growth rate and you want the unit multiplier, this is how we'll do it. If you want if I have it the other way around, if you have your unit multiplier and you want the continuous growth rate, just solve for r. And so we'll see that r is the natural log of b. Since we can also write this as m to the 1, since we can also include m to the x over k, or m to the 1 over k to the x. If we happen to have some unusual multiplier, we could say that m to the 1 over k is equal to e to the r. So from here, we would want to write, I don't really need this one, but it's fine. So we might want to write, it's going to replace the B. I don't like this one sitting in the line. Get out of here because you're not solved for any one piece. Since B is this m to the 1 over k, I could say that the continuous growth rate is the natural log of m to the 1 over k. That's more like it. So if we, in our previous example, where we had y is equal to a, I'll use that for no particular reason, times 2 to the x over 10. Actually, I want to take that number out of it. I just started. So here, y is equal to a, whatever we start with, and we're multiplying by 2 every 10 units. We found out that this was equivalent to approximately 1.072 every 1 unit. So double every 10 units, or increase by 7.2 every 1 unit, or if we find a continuous growth rate by taking the natural log of 2 to the 1 over 10, we get 0.0693. It's 1/10 natural log of 2. So we might read this as y is equal to a when x equals 0, and y increases continuously at 6.931% per unit. Is everybody okay? So yesterday we looked at an example where we're adding up a very long. So we looked at an example where we deposit, let's say, $1,000 into an account that increases by 10% each year. Oops. Deposit that $1,000 every year into account that increases by 10% each year. And then we worked out what this would be using a little bit of algebraic sleight of hand. Oh, whoops. This is off by 1 because we start the counting at 0. So if we wanted to do this for multiple years, or what we want to be able to do, we can also model this with continuous growth. So this is just increasing by 10% every year. We could turn that into a continuous growth model. Our continuous growth rate will be the natural log of 1.10. 1.1 is our unit multiplier, because we're increasing by 10%, so multiply by 1.1. And if we take the natural log of that, that will give us our continuous growth model. Now, what we were doing yesterday was adding up a bunch of terms. What we were doing yesterday was adding up a bunch of terms. Adding up a bunch of terms. What is it in calculus when we want to add up a bunch of terms? If we want to approximate the value after a bunch of years, we can imagine this with a continuously compounding model. And instead of just adding up a bunch of terms, we could add up a bunch of terms. Integrals represent multiplication, but one of our factors is continuously variable, so integrals represent addition. So if we're adding up a bunch of terms, why don't we approximate that with an integral, especially considering what we're doing? So when n equals 10 years, if I approximate with oops. So if I do I'm going to give myself this number. So now if I press R, then I have it. I have now a natural log of 1.1 button on my calculator. So I want to math 9 for an integral, and I want to put $1,000 a year in an account that's going to be increasing continuously at a rate of 9.5% for a bunch of years. We'll integrate with respect to x from 0 to 10. So after 10 years, we'll have $16,721.64. That's just after 10 years. After 20 years, I'm just going to do the same thing, but change the 10 to a 20. We'll have $60,093. Doing an approximation, I don't know why I'm going all the way down to a penny. After 30 years, $172,588. And after 40 years, $464,370. So the amount of growth that we see, the amount that we're putting in The investment part of this, that's increasing linearly. The increase, if we subtract off the 10,000 that we put in, because it was 10 years at 1,000, we have an increase of $6,721. If we subtract at 20 years, we've only put in $20,000. We have doubled the amount that we put in total, but now our growth is $40,000. If we subtract off the $30,000 that we put in at this point, it's a growth of $142,000. And here, even though this total is almost more than twice as much as the 30 years, we've still only put in another $10,000. So the amount that we're putting in is going up linearly. The amount that we're getting out is going up exponentially. The most powerful piece of this problem is the time that we have. And the best time is these first 10 years. It doesn't look good after that first 10 years, but that first 10 years, if sitting from 30 to 40, is a big deal. Does that make sense? So if you think about retiring at 60, this is your retirement if you start at 20 years old. This is starting at 30 years. This is starting at 40 years. This is starting at 50 years when it doesn't even matter. Like, it'd be pointless for me to start brand new an account, except for the fact that I have more money that I could dispose of and put to sleep for the next 10 years. Any questions? Notice that this was only $1,000 per year. This is us maintaining only $1,000 per year for those 40 years. That's like $83 a month. Presumably, at some point along the road, we'll find more room in our budget to increase the amount that we're putting away. So we would adjust our model to $83 a month to $2,000 a year, $160 per month. Now notice that this 1,000 is just sitting there as a multiplier. So if I change that to a 2,000, if I double this coefficient, that just doubles all these values. Now, if I double this coefficient halfway through the process, then I just have to do two separate integrals, one with the 1,000 coefficient, one with the 2,000 coefficient, but the basic idea still holds. The best years, if you're planning for a retirement, the best years are the ones furthest away from that retirement. That's why I say you should start now. I don't have advice about how you should go about that exactly, because I am not a financial professional. And you would never want to give legal or financial advice. But I am saying that the best years to start your retirement account are now, when you're furthest away from retirement. If you start thinking about it at 50, you're going to be too late. That makes sense? Now, you might be like, oh, the world is going to be ended in 50 years, so I'm not really worried about it. So, I mean, fair. But even if it sounds like a lot, even if you're like, oh wow, $10 is a lot, $10 is more than zero. Because if I change this coefficient to a 0, then the end result is 0. Make sure you get an employer that matches 401k, and make sure you max out your 401k. Like, you might not, does anybody know what 401k is? 401k is a retirement account. Or your Roth IRA. Get a Roth IRA or a 401k and make sure, and find out if your employer does contributions. That one maxes out. A 401k, you max out your contributions. Right. All right, that's going to do it for today. I know that wasn't really a calculus thing except for this integral at the end, but there, it's calculus. That's it for today. I'll see you all on tomorrow. Everybody have a good day. Start a retirement account, and thanks for playing. Have a good day.